strategy which we will follow in describing radially symmetric perturbations and radial symmetric pulsations. So we can restrict ourselves in the following lectures to considering radial pulsation. Everything is spherically symmetric. The background model, the stellar model, of course, is always spherically symmetric. Any other models do not yet exist. So apart from the stationary, from the hydrostatic stellar model, also the perturbations and the following pulsations are spherically symmetric. Well, we have split, or we are going to split our approach into three parts. First of all, or the first step would be we construct a stellar model. This can be done by means either of stellar evolution calculations or by a simple envelope integration, where we can put the star at the observed position in terms of luminosity and effective temperature. We assume a more or less well-known mass, chemical composition is observed, and then we can construct a model which is restricted to the envelope of the star, which excludes the center of the star in which nuclear processes can take place. So this is a nice and easy alternative to do full stellar evolution calculations. Well, the difference between stellar evolution and the pulsations is that for stellar evolution we assume hydrostatic equilibrium, acceleration is 0, and for the pulsations we assume the opposite. The pulsations are characterized by deviations from hydrostatic equilibrium. We have a finite acceleration then. Opposite or contrary to the stellar evolution, now the nuclear timescale is ignored because the nuclear processes occur on a much longer timescale than the pulsations. The same is partially true for the thermal timescale, and we will see in the following when the thermal timescale has to be taken into account. Somehow the mouse does not work. Can I shift down a bit? Okay, now it's okay, it's again. No, I don't. Okay. Okay, that's so. Now the next step in the approach will be that which is motivated by the observations. The pulsations are seen to keep the mean properties of the star the same, so the mean luminosity will remain the same as without pulsations. The mean temperature is the same, the mean radius will be the same, and the pulsations may be regarded as a superposition of variations or oscillations around the equilibrium. Okay, that means we are dealing with small changes. Small means changes of the respective quantities like luminosities around the mean or the stationary value. So these pulsations are small variations of the mean quantities. Pulsations are described as small time-dependent perturbations of the time-independent stationary or hydrostatic stellar model. Okay, so this general strategy, as I already said, will be first of all, at the beginning of a stability analysis, symmetry, and we are left at the end. Here we are. These are the equations which we have to solve. The mass conservation equation, then the momentum conservation equation. Without the acceleration term, this would correspond to stellar evolution. Pressure keeps gravity in equilibrium, and this term is 0. Now we switch on this term here. This is new. And then we have the second, the energy equation, dL by Where is the mouse? Okay. Okay, the energy equation, which is describing the nuclear energy production. This may be, the energy production may be ignored in some cases. We will account for this term even for stellar pulsations, and then we have this term which is related to the thermal time scale. It is taken into account for stellar evolution, of course, and it's also partially taken into account once we consider stellar pulsation. And one of the most important equations is the equation of energy transport here in the diffusion approximation for photon diffusion, and the equation which is considered in stellar evolution is the blue one. This accounts for the change of chemical composition by nuclear reactions. This equation is ignored for stellar pulsations because nuclear reaction take place on a much longer timescale compared to the pulsation timescale. So this is ignored, and we have to consider these four equations: mass conservation, momentum conservation, energy conservation, and energy transport. And we take into account the thermal timescale, this time derivative with respect to the thermal timescale, the time derivative with respect to the mechanical acceleration, and then we will end up with the equations that govern the radially, the spherically symmetric pulsations. Okay, we assume that our quantities, well, these equations have been solved with respect to zero acceleration, so we can assume that there is a quantity T0, like the Q0, L0, for which this equation has been solved, and we know the solution, and which we know the hydrostatic solution. We can assume that T0 and L0, R0, and so on, P0, are known quantities as a function of the radial coordinate mr. And now we enter this equation with the assumption that Q0, that some Q, some value for L, is given by the sum of the hydrostatically determined value plus some perturbation, which is now time dependent and spatially dependent. So we entered these equations with saying, for instance, for T, we replace, or let me give an example here. For example, this is the easiest way here. Let's take this equation here for the hydrostatic equilibrium. So we assume first that this equation has been solved by stellar evolution, for instance, and we have dp0 by dmr is equal to minus gmr over 4 pi r naught to the fourth. So we have the values of p naught and r naught, and they satisfy this equation. These have been determined previously or previous to our pulsation analysis. This term is 0. Now what we do, we say P naught, or P, the pressure is P naught as a function of mr plus P1 time as a function of mr and T. And we insert this into this quantity. So we have that this dP by dmr is replaced by dP naught by dmr plus dP1 by dmr. And we do the same here on the right hand side. Well, there is this factor 1 over r to the fourth, which is left here. Well, this has to be expanded in terms of a Taylor expansion. 1 over r to the fourth is, so the right hand side is minus gmr, I will do it here on the blackboard to illustrate it once how this is done in detail. 1 over 4 pi times r naught plus r1 to the power 4 plus, now we have, in addition, we have this acceleration term, which is given by minus 1 over 4 pi. We replace r squared by r naught plus r1 squared, r naught plus r1 squared times the acceleration. This would be here times acceleration. I hope you can see it. The acceleration is d2 by dt squared of r naught plus r1. What is the second time derivative of r naught? Pardon? That's 0 because r naught is a hydrostatic quantity, so we can drop this here. So this is simply a quantity which is only going with r1, with a perturbation. That's because r naught is time independent. What about this quantity 1 over r naught plus r1 squared, and we have these quantities twice, which look similar. 1 over r naught plus r1 to the power minus 4 and the power minus 2. Well, these are done in the following way. So 1 over r naught plus r1, take this to the power 2. We take out of this bracket, we take 1 over r naught squared times 1 plus r1 over r naught to the power 2. Okay? So now we know, we assume that r1 and r1 is small compared to r naught. This is our assumption. R naught is a small quantity, that means r naught over r1 is small compared to unity. So we can expand this quantity around the value 1. So this is 1 over r naught squared times what is 1 over 1 plus r naught squared. How does the power series go for this quantity? Pardon?
1 minus 2 r1.
Yes, okay. That's known to everybody? Okay? You're familiar with that? Okay, so I don't need to explain. This is a simple Taylor expression. It's 1 minus 2 times r1 over r naught plus, next term would go with a term which goes with r naught plus r1 plus something. Well, there's a plus coefficient. We don't need to consider it. The next term goes with r1 to r naught squared, and we assume that this r1 over r naught is a small quantity, so we can drop this because it's of second order. Okay, so we have the following relation here. We have well, for 1 over r naught plus r1 to the fourth, we will have the linearized version 1 over r naught plus r1 to the power 4 will give a similar result. This is 1 over r naught to the fourth times 1 minus, not 2, but minus 4 times r naught, r1 over r naught plus terms which we will ignore because they are of higher order than the linear term. So what we are left with here is then, what about this quantity here? We have 1 over 4 pi r naught plus r1 squared times the second derivative of a quantity which is already of first order. We have d2 by dt squared of r1 here. So what does it mean for this coefficient? Do we need to consider this r1 here? we don't need to consider it because this is already of first order, so it can only be multiplied with a stationary value. Otherwise, we would have a term of second order in the perturbations. So we drop this here. We can ignore it because this would give a term which is of higher order in the perturbations compared to linear one. And only here we have the -4. This is going to gm over 4 pi r naught to the fourth times 1 minus 4 times this quantity, 4 times the first order perturbation of the radius. So let's do it once again here. So we have as a result of the perturbation of the mechanical equation, we have on the right hand side we have dp naught by dmr plus on the left hand side we have dp naught by dmr plus dp1 by dmr is equal to minus gm over r to 4 pi r naught to the fourth times 1 minus 4 times r1 over r naught plus or minus 1 over 4 pi r naught squared. We only need to take the unperturbed quantities times d2 r1 by dt squared. Okay, so this is the expansion of the hydrostatic or the mechanical equation. This is an expansion of the hydrostatic equation around the equilibrium, and we're going with the perturbation to first order, neglect all higher order terms which are of higher order than linear in the perturbations. Okay, what we observe here is then, well, if we take the first term here, then we have dp naught by dmr for the hydrostatic value, and here we have minus gmr over 4 pi times the radius to the fourth times 1. Well, these two terms, what do they do? This one and this one, the first contributing to the 1 here, they have to cancel because for the quantities with index 0, we have that this have to be they have to satisfy hydrostatic equilibrium. So dp0 by dm has to be minus gm r over 4 pi r0 to the fourth. So these two cancel, and we are left with a homogeneous linear differential equation for the perturbations here in terms of p1, r1, and here r1 is appearing in the acceleration, and we have kept the time derivative of this perturbation, and we have kept the linearized version of the hydrostatic equilibrium. That's how we linearize this equation, or how we insert our assumption that the some quantity is to be split in a hydrostatic value, which we know, and a perturbation value, which is taken into account up to linear order, higher order quantities in terms of the linear or the perturbations are neglected. Is that clear to everybody? I wanted to do it once in an explicit way to let you see how this procedure is performed and how it is done. If there are questions, please ask. Okay. So we go back. This procedure will now be done for all of these equations, and we'll see what the result of this linearization, the process which we are doing now, is the linearization of these equations, linearized around some hydrostatic solution which we have determined before in the beginning of the analysis. Can we now go back to the previous file? Okay, this is the strategy. the general strategy for our... Okay. Okay, we neglect terms of high second or higher order in the perturbations, and as a result, the equations become linear with respect to the perturbations Q1. The process which the process which we are doing is called the linearization of our equations. Well, we obtain homogeneous linear equations for our perturbations P1 and R1. Once we multiply such linear equations with an arbitrary factor, what happens? If we have a solution in terms of P1 and R1, if we multiply them by a constant factor, then they will also be a solution of the problem. That means linear equations are always determined, the solutions of linear equations are always determined only up to a constant factor. That means, with respect to the physics, once we have a linear theory for the perturbations, we can superpose any of these solutions and it will give us a solution again. Is that clear to everybody? That means, also on the other hand, that we cannot determine the amplitude of a perturbation. Because we can always multiply any solution with an arbitrary factor, then it will become a solution again. That means the amplitude of the solution cannot be determined in principle from a linear theory. Okay? This is a drawback, a major drawback of this linear theory. Keep in mind, you can never determine amplitudes of a perturbation or of the solution of the perturbation equation, because the amplitude is in principle arbitrary. You can always multiply a solution with an arbitrary factor. It will become a solution again. Okay? Amplitudes, keep in mind, amplitudes can never be determined by this approach. Okay, so what shall we do then once we cannot determine amplitudes? Well, this will be the third step of the analysis of the general strategy. Once we found a linearly unstable mode, a mode which, or a perturbation which is unstable according to the linear theory, then we need to do some nonlinear stuff, of course, because only the nonlinearity can be used to determine the amplitudes. So once we have a linearly unstable model, then we have to follow the evolution of such an unstable perturbation into the nonlinear regime once the terms, at least the terms of second order in the perturbations, come into play, and then then determine the amplitude. So the third step, if we have done all that linear stuff, then the third step will be follow the evolution of the instability into the nonlinear regime. This can only be done by numerical simulation. So we have to do numerical simulation, and we have to solve the full set of the equations which we have seen just before. There is no change in the equation. We just take these equations and put them in the computer with an appropriate numerical scheme and numerical code, and then we solve the complete set of equations without restrictions to the amplitudes or without restriction to the magnitude of the perturbation, and then we may derive the amplitudes and the final fate of an unstable model. Well, this is the third step then. We will now in the following consider first the linear theory, and finally at the end of the lecture we will come to the third step, which consists of following or numerically simulating the evolution of an instability into the nonlinear regime and to determine the final amplitudes of our perturbations. Okay, so the strategy falls into 3 steps. Construct a hydrostatic stellar model, do a linear stability analysis, and the third one, once you have an unstable model, then you follow the evolution of the instability into nonlinear regime and determine amplitudes. And if the instability is very strong, you may not even be able to determine the amplitude, but the star may get disrupted by an instability, so the final fate will not be a nicely pulsating star, but it might be that the star gets disrupted by an instability. Both can happen, but the third step will then be the nonlinear evolution in any case. Okay, questions about that? So the next step we consider is then the linear theory and the linearized version of our equations. Okay, so that's the strategy. Now let's go to the linear radial stability and pulsations. Well, we assume, of course, as said before, we assume a hydrostatic model to be provided by R0 as a function of m, P0 as a function of m, density, temperature, luminosity, and so on, as a function of the radial Lagrangian coordinate being time-independent quantities. Well, our approach is then to assume small perturbations to it. So we say R is R0 as a function of m plus the perturbation R1 depending on mass and time, the same for the pressure and luminosity and temperature and so on. So we insert these into the time-dependent equations. We have seen these before. If necessary, we have to perform a Taylor expansion around the hydrostatic or the stationary values. Let's here do it as an example for the density. That might be more instructive than the linearization I have shown you in detail before. So we write the density in terms of rho naught plus R1, split it into the hydrostatic and the perturbation type. This is in general a function of pressure and temperature. So this is a function of P0 plus P1, T0 plus P1. This is, according to a Taylor expansion, the value of the density at P0 and T0, and that is of course our rho naught. So the rho naught will cancel. If we compare the left-hand side and the right-hand side, you see the rho naught of course cancel, and this will give an expression for the perturbation in density rho 1. So let's perform this Taylor expansion. Then this is the derivative of the density with respect to pressure times the perturbation of the pressure plus the derivative of the density with respect to temperature times the perturbation in the temperature. Now these are already quantities of first order. Of course we can drop the second order quantities according to our assumption that the perturbations are small. Well, then the coefficients or these derivatives, because this is already of first order, this can be taken at the stationary model or at the zeroth order for the zeroth order quantity. Because if we take here somewhat more than the background or the original value, then this would be of first order. So we would have a second order term. To keep it a first order term, this can be evaluated with the index 0. It's clear to everybody? So because this is already a first order quantity, then this needs to be a zeroth order quantity, or it's sufficient to have a zeroth order quantity, plus terms which go with the pressure perturbation and the temperature perturbation squared. Okay, so if we redo this equation, or we reformulate this equation divided by rho 0, so going to relative, the relative quantities, rho 1 over R0 is then in terms of P1 over P0 and T1 over T0, we go to the relative quantities, relative pressure perturbations and relative temperature perturbations, then this is our famous well-known quantity d log rho by d log p in the stationary, for the stationary value, so with index 0, because this is already of first order. In the same way, this is our coefficient delta taken at the background model or at the stationary model. That means with index 0, because it's clear that we have to have the index 0 here. We drop the index 0 here, and you have to remember that this is referring to the stationary model, these alphas and deltas. So we know these alphas and deltas because they are predetermined by the hydrostatic stellar model. Similar for the 1 over r squared. I have shown you this explicitly on the blackboard, how it works. So this 1 over r squared is linearized in this way. So now we go into the equations. Neglect the quadratic and higher order terms in the perturbations, and you make use of the hydrostatic equation. I have shown this explicitly here because here the stationary pressure gradient cancels the gravity on the right hand side here. That's what is meant with making use of the hydrostatic equations for the Q naughts. Okay? Well, let's continue. What do we end up with? Okay, first of all, mass conservation. We are left on the left hand side with the derivative of the perturbation of the radius. It's a dependent quantity, is given by minus 2 times perturbation of radius divided by 1 over 4 pi rho r cubed. Well, this comes from the linearization of 1 over r squared. We have dr by dm is 1 over 4 pi rho r squared. This is a linearization of the 1 over rho squared, 1 over r squared term, and this here is the linearization of 1 over the density. Once you linearize 1 over density and express it in terms of the pressure and temperature variation, then you get this term which goes with alpha times pressure perturbation, like the linearization of density you have seen before. Alpha times p1 over p naught minus delta times the relative temperature perturbations. So this is again a homogeneous linear equation with concerning linear equations for the perturbed quantities as coefficients for our perturbations, and the equations are linear in the perturbations. Well, I have explicitly shown you how to derive the momentum, the linear momentum equation. That's here. We have this 4 dp by dm by dp by dm. This is the 1 over r to the 4th linearization, and this here is the acceleration term, where the acceleration is a first order quantity itself, because r naught is not time dependent, and then this can be taken as a quantity in the hydrostatic model. So we have to take only 1 over 4 pi r naught squared here. I've shown this explicitly on the blackboard, so I don't need to comment on this anymore. Well, there is a plus 4, and the plus 4 comes from here. The minus and the minus cancelled, so this is plus 4 here. Okay, energy conservation will be the next equation which needs to be linearized. Okay, this is energy equation. So in that case, we have to linearize the both the gradient of the luminosity. You recover you recover the original equations here, and you have, because the derivatives are again a first order quantities, you have to take the derivative of the entropy which is behind these time derivatives with coefficients which do only depend on the stationary, on the hydrostatic model. So this gives minus Cp at the hydrostatic model, the specific heat in the hydrostatic model, times the time derivative of the temperature perturbation plus delta naught over rho naught, quantities in the hydrostatic model, times dp1 by dt. And once you linearize the energy generation rate, if you want to take it into account, then this is given by the energy generation in the hydrostatic model times some coefficient which corresponds to the logarithmic derivative of the energy generation with respect to pressure, or with the logarithmic derivative of the energy generation with respect to temperature, which have to be multiplied with the relative perturbations of pressure and temperature here. Well, this is simply linearization, which is done very well, or in the same way as it's done for the density. And we have, for the density we get here, we simply have to replace the derivative of the density with respect to pressure and temperature by the derivative of either the energy generation rate or the opacity with respect to pressure and temperature. And we get very similar relation. So we get something like kappa 1 or epsilon 1 over rho 0 will be the logarithmic derivative of the energy generation rate or the opacity times the pressure perturbation plus the derivative of the energy generation rate or the opacity instead of the density. Otherwise, it looks very similar to this linearization of the equation of state. So it is done very much the same way as the density is linearized using the formal prescription of an equation of state, rho as a function of pressure and temperature. So it can be done very much the same way for the energy generation rate and the opacity kappa. And we are left then with logarithmic derivatives of these quantities with respect to pressure and temperature. They are denoted by epsilon p or epsilon t, epsilon sub p, epsilon sub t, or kappa sub p, kappa sub rho. That's how these logarithmic derivatives of opacity and energy generation enter the equations. Where is... Okay, so these are these logarithmic derivatives, epsilon p and epsilon t. They have, of course, to be taken from the stationary model, because p1 and t1 are already first order quantities. So if you want to consider the epsilon terms, then they have to be taken into account in this way. Well, energy transport, that's the most complicated version of this equation. Well, we have on the left-hand side, we have to linearize the temperature gradient. On the right-hand side, we have one term. This is essentially the diffusion coefficient. And if I may remind you how the diffusion coefficient, or the terms on the right-hand side of the energy transport equation look like. Well, this is dl by dmr is something like minus. There is an L here, and there is a 1 over t cubed there. There is a 1 over kappa here. There is, what else is left? There is a 1 over r to the 4th left here. We need to linearize this term. This gives, in terms of the linearization of the luminosity, will give a term proportional to L1 over R naught. This is that one. Then we have 1 over r to the 4th. This gives a minus 4 times the perturbation of the radius. And then we have the opacity. Well, the opacity then gives you some of these logarithmic derivatives, like the density which we saw before. This is kappa p. This is the logarithmic derivative of opacity with respect to pressure times the pressure perturbation and an additional term or a comparable analog term with respect to the temperature. So this gives the derivative of kappa with respect to temperature times the temperature perturbation. So these are the linearized version of luminosity, temperature cubed. Temperature cubed is this factor of 3 here. So this gives a factor of -3 times the temperature perturbation kappa, and this is the radius. So these are the linearization of all the terms on the right hand side. Okay, and for simplicity, we have taken out of this bracket, we have taken out some of the quantities referring to the hydrostatic model, which is essentially the pressure gradient, temperature and pressure, and the nabla 0, which is the nabla, the d log t by d log p for the stellar model, for the hydrostatic model we have determined. So this is d log t0 of d log p naught. We keep in mind it's not the radiative nabla, it's not the adiabatic nabla, it's the nabla, value of nabla for our specific model we have determined previous to the stability analysis. Okay, here the definition of kappa p0. All these quantities have to be taken or to be applied in the hydrostatic models because they are multiplied with terms of first order. So these are the definitions of nabla 0 and the kappa p's and the kappa t's. Well, there's one issue here, one point I should mention. Well, this is now, if this term would be absent, if this would be unity, then this would be the linearized form of the diffusion equation for energy transport by diffusion of photons. Now we have the situation that in our star we do also have convection. And I told you there is a engineering prescription once you try to consider or try to calculate convection for hydrostatic stellar models. This is a mixing length theory, but we don't really know what to do when convection is present in a time-dependent environment. So if there is convection in our star and we are considering pulsations, then we somehow have to treat or to deal with the convection, and actually there is no real theory and no real satisfying approach for that. One of the approaches which is nevertheless used is the so-called frozen in approximation. Well, what is the frozen in convection? This approximation assumes that the convective flux is constant during a pulsation period. So the convective flux does not react on the pulsation. What could be a justification for this assumption? Frozen in approximation means the convective flux is constant during one pulsation period, or is constant on the time scale of the pulsation. What would be how could you justify this approximation? Some idea? Well, if one considers the time scale of convection and the time scale of pulsation, if the pulsation is much faster than the convection, then we might assume, or it seems plausible or reasonable to assume that the convection will not have time to react, so the convective flux will be maintained during a pulsation period. That's actually the justification of this frozen in approximation. So we have to ensure that once we take this frozen in approximation, that the pulsation is much faster than the convection. What about modes which have the same time scale as convection. We'll see later on that there are modes. In particular, those slow modes, which are typically the G modes, they have periods comparable to convection. It's highly doubtful how to treat them. You can assume, or you can justify with a plausible arguments, that for fast pulsations like P modes, we will find out later, for P modes and for fast oscillators, the convective flux doesn't have time to react, and the convective flux is maintained during a pulsation cycle. That means the convective flux is constant, or the perturbation of the convective flux is zero. And once you apply this frozen in approximation, you can do it explicitly, then you will get another factor of order unit here in front of the luminosity perturbation, because you don't perturb the entire luminosity, but only the fraction of the luminosity which is transported by radiative diffusion, and you ignore the fraction of luminosity that is transported by convection. And in that case, you get the ratio of the total luminosity, that's including both the radiative diffusive luminosity plus the convective luminosity. This is the total luminosity and the fraction of the luminosity which is transported by radiative diffusion. This is called the radiative luminosity in the stationary model. In the stationary model, you determine both the total luminosity, the radiative luminosity, and the convective luminosity. Convective plus radiative gives the total luminosity. So you have to multiply this with a factor of the ratio comparable to the ratio of the total luminosity and the fraction of the radiative luminosity. This is the result of a consideration of the frozen-in approximation, which tells you, or which assumes, that the convective flux is constant during pulsation, or the perturbation of the convective flux is zero. Okay, so this is an additional factor which can be taken into account once we have a convective zone in our star. Usually you would not like to consider stars which have big amount of convection. You look usually how big is the fraction in the convection zone which is transported by convection, and you will limit your consideration of models to stellar models which have convection zone where not more than 50%. I would say this is also already very much, where at least in a section of the star only a fraction of less than 50% is transported by convection. So if convection anyway contributes only, say, 10 or 20%, and you assume, or you take into account convection by frozen-in approximation, you will not make a big error in your computations. But convection, again, I have to tell you, it's a big problem in stellar pulsation and in stellar evolution, and there are some more or less plausible assumptions to treat convection in the framework of both stellar evolution and in stellar pulsation theory. Okay, so that's this is the result of the linearization of our equations. We have done stellar evolution, or determined or constructed a background model, a stationary, hydrostatic, stationary, time-independent model. And these are the equations which describe small deviations from this hydrostatic equilibrium, which are to first order linear equations, and we now try to solve these linear equations. Well, we cannot hope that there are analytical solutions to that equation, so we have to solve the system of the equations numerically. I think I have to stop here. Okay, we have a break.
So we are going to resume our next session at 11:30. Okay, so we'll have a break of 15 minutes, and then after that we'll resume the session at 11:30. Okay.
Okay, welcome back. Well, we have derived now the equations which govern small perturbations around the equilibrium for a star. So we have determined the hydrostatic structure, the time-independent structure, and we were considering the time-dependent perturbations, the equations governing time-dependent small perturbations around the equilibrium. That means we have derived the linear equation, we have done the linearization of the problem, and we have derived the linear equations for the pulsations. Okay, we have to solve this system of equations linearly, and so we have to prepare, or we have to make them treatable by numerical methods. The first one we do, we go to relative perturbations, so we have to make everything dimensionless. We have already done it here. We refer to the relative perturbations in terms of P1 over P0 or T1 over T0. Means we take the ratio of the perturbations of the perturbations and the background model, and this for all quantities occurring here. Okay, this is first one, introduce dimensionless variables. Zeta is the relative perturbation of radius, or in other words, the relative Lagrangian displacement. Keep in mind we are in the Lagrangian framework, so we have adopted implicitly here the Lagrangian description. Small t is simply the relative temperature perturbation, small p is the relative pressure perturbation, and small l is the relative perturbation of the luminosity. Then to gain maximum resolution, we usually take as an independent variable not the mass mr, but we go to log p0 as an independent variable. Why is that done? Well, in an atmosphere or in the stellar envelope, in the outer stellar envelope, usually there is not much mass in there, but the pressure varies quite by several orders of magnitude. So to gain resolution, it's better to go to a quantity which varies much in the outside of the star where the pulsation takes place, and go to some go from the mass, which does not have a big range in values in the outer part of the star, to go to the logarithm of the hydrostatic pressure P0. The transformation is found through the hydrostatic equilibrium of the background model. That means dP0 by dmr is given by minus gm over 4 pi times the radius to the 4th power. And by taking the differentials or comparing the differentials, the transformation is done by d by dmr is transformed through this factor times d by d log p0, the factor which connects the derivatives with respect to mass, and logarithm of the background pressure is given by gmr over 4 pi p0 times r0 to the 4th power. This is done for numerical purposes to achieve maximum resolution, or to achieve good resolution in the outer parts of the star. Nothing else. It has no physical background. It is done for numerical reasons to increase the resolution. And hereafter, the d by d log p0 will be denoted by a dash. Well, how shall we make the time coordinate dimensionless? Well, one obvious or one plausible way to get dimensionless time units would be to measure the time in units of the dynamical time, because we expect the pulsations to operate on the dynamical time scale. So it might be a good thing to do is to measure the time in units of the dynamical time scale, or in other words, dynamical time scale means the star is expected to follow the period density relation to normalize periods by the period density relation, which would be an equivalent way to formulate measuring times in units of the dynamical timescale. Okay, the dynamical timescale is nothing but the square root of g times the mean density of the star. This is also what is contained in the period density relation. So we go from time t to a dimensionless time tau by dividing or by multiplying, dividing the dimensionless times by the dynamical timescale, which is square root of 4 pi times gravitational constant times mean density. Well, we will only occasionally be dealing with the energy generation and its influence on pulsations, in particular on the driving of pulsations. Therefore, for simplicity in the following, we will omit the epsilon terms. Once we talk about the so-called epsilon mechanism, we will consider them again, but for simplicity in the following, we will drop just the epsilon terms in the energy equation. There's no physics behind it, it's just for convenience. We drop them because in general we will not consider or not comment on these epsilon terms anymore. There is just a few places where we come back to this term again. Okay, so what happens then? We end up then with the LNA equations, linear non-adiabatic equations for mass conservation, for momentum conservation, for energy conservation, and finally for energy transport. So let's have a look first for the mass conservation. So zeta dash is given by some coefficient, by some dimensionless coefficient, which we call C4 times 3 times zeta plus alpha p minus delta t. These are the coefficients of the equation of state. The 3 comes from the 1 over cube dependence of the mass conservation equation, and then there is a coefficient C4 which is given here in a dimensionless form. All these quantities are dimensionless. Time is measured in units of the free fall time of the dynamical time scale, and all the other quantities are relative quantities, so these are all dimensionless quantities. Momentum conservation, if we go to relative perturbations, then p dash is equal to minus p minus 4 times zeta plus dimensionless coefficients c3 times the acceleration terms d2 of zeta by d tau squared. This is the momentum conservation equation. The energy equation is given by the derivative of the luminosity perturbation. It takes a while until it reacts. Doesn't come down. Sorry. Now it's done. Okay. The derivative of the luminosity perturbation is given again by another dimensional coefficient C1 times 1 over nabla adiabatic. This is our famous d log t by d log p at constant entropy. This is nabla adiabatic determined from the equation of state. And of course, because it's multiplied with the first order quantity, this has to be evaluated in the stationary, in the background model, in the hydrostatic model. So nabla adiabatic evaluated in the background model is d log t by d log p at constant entropy. So this is the energy conservation equation where we have dropped the epsilon terms. This would have been the only place where the epsilon term would occur. Then more important or most important is the energy transport. Well, the energy transport is given in terms of the derivative of the relative temperature variation. This is given by nabla naught, or nabla, the value, the stratification, the nabla naught, determining or characterizing the d log t by d log p for our actual stratification within the star. So this is determined from with reference to the actual stratification of our model times, in case where we have transport by energy, transport by convection, and take it into account according to the frozen in approximation. Then we have the ratio of luminosity to radiative luminosity in the convection zone times the relative perturbation of the luminosity minus 4 times the Lagrangian displacement, relative Lagrangian displacement, and these two terms involving the derivatives of the opacity with respect to pressure and temperature. So what we have done is simply a normalization of our equations, a transformation to convenient variables, and making the equations dimensionless with a dimensionless time and dimensionless variables and coefficients. All the coefficients are now dimensionless. Well, we have introduced here 3 coefficients, 3 dimensionless coefficients, which we need to discuss. So these are coefficients which determine on the properties of the hydrostatic stellar models. These are, first of all, C4, and then C3 in the second equation, and C1 in the third equation. All our quantities are known, which refer to the equation of state coefficient and the opacity coefficients here. So what are these dimensionless coefficients? Well, let's go first to C3. C3 measures, so in some sense, the mean mass contained in a volume of radius r0 to the actual mass contained in a volume of this size. So it's some kind of mean mass divided by the actual mass coordinate. So this is a coefficient of order unity. It doesn't vary too much. It's a quantity which is of order unity and describes, so to say, the stratification of density. So it's only the density which matters, which influences this coefficient 3. There's not much behind it. It describes the stratification of density. Well, the C4 is then defined as P naught times R naught over GM over rho. So what is that actually physically? Do you see what this means physically? It contains P naught over rho naught. This is the sound speed squared. And GM over R is the gravitational energy. So it relates to some sense a kind of acoustic energy to the gravitational energy. How does it go once with radius? Once we consider this, so P naught and rho naught, once we approach the center of the star, they will approach a finite value. The mass close to the center goes with which power does the mass go close to the center? Does anybody know? Mass is mr is the integral rho r squared dr, 4 pi. So the density goes to a constant value somewhere in the center. It's finite. So mr is the integral over r squared. So mr goes like r cubed if we approach the center. Okay? Because the density has a finite value. So this goes like 1 over r squared. So this coefficient diverges for approaching the center. So this coefficient becomes infinite if we get close to the center of the star. Well, there is one coefficient is left, which is the coefficient C1. Well, this contains, first of all, it contains the mean density, or so to say, the dynamical timescale is contained in here. It contains some of the thermal quantities because it's the equation for thermal energy transport. Well, it contains equation of state coefficient, which are of order unity, density, pressure, the radius, the mass, and the luminosity. Well, how does it go around the center? What is the behavior of the C1 once we approach the center? Once we go to R0 equal to 0? Well, delta rho, the mean density, and pressure will have a finite value once we approach the center. But what about the mass and the luminosity? The mass we have already seen. The mass goes with r cubed. What about the luminosity? dl by dm. dl by dm is epsilon. So L goes, if we bring it to the right hand side, L goes with epsilon times mr once we are close to the center. So L has the same dependence on radius as the mass. So L also goes with r cubed. So this term will go with r to the 6th power times cancels with the r to the 4th power. So this coefficient also goes to infinity if we approach the center. It goes to infinity with 1 over r naught squared. Well, that's a little bit a problem if we want to solve these equations numerically. In other words, once these coefficients diverge, if we go to the center, well, what we'll do then, we bring it to the left-hand side. So we take C1 here and bring it to the left-hand side, so we have 1 over C1. Of course, we would like to have all quantities. In order to be able to interpret them physically, they need to be finite. We cannot interpret infinite quantities in physics. We also always want to have finite quantities. So we must assume that the solutions of our equations remain finite all over the integration interval. Otherwise, we cannot use them for physics. Well, so the solutions and all quantities appearing here. Well, here it's all fine, all quantities, even the coefficients of the equation, of the perturbation equations are finite. This is true here as well, except for the coefficient C1. So let's bring it to the left-hand side in that case. Then it goes to 0 once it's used as a coefficient of the derivative of the luminosity. So we have on the left-hand side, we have something like that. On the left-hand side, we have 1 over C1 times L dashed is equal to the bracketed term, but don't need the bracket, 1 over nabla adiabatic times the dt by d tau now minus dp by d tau. Okay. And same is true, or the same will be done for the first equation, where we encountered a diverging coefficient. Where is it? Well, this equation is okay. No singularity, all the solutions are required to remain finite. But here, this is fine, the bracketed term is fine. And on the left hand, we bring this C4 to the left-hand side, and we get 1 over C4 times zeta dashed is equal to the bracketed term. So we have, nicely, we have all coefficients now finite everywhere. All the solutions are finite everywhere, but we have zeros both for the first and the third equations, zeros at the highest derivatives of the respective equations. So the coefficients of the derivatives vanish at the center. And this situation is called a singular point of the equation, of the differential equations. Are you familiar with singular points of a differential equation? Do you know what it is? some of you do know what it is, but it seems not everybody is familiar with the concept of a singular point. So it means everything is nice. For physical reasons, we need to have all solutions to remain finite. So we would also require the solutions to be finite at this singular point. And singular point means the derivative, the coefficient of the highest order derivatives become zero somewhere, and this zero, or this singular point, is a member of the integration interval. Actually, it's the center of our star. Okay, so we have two equations where we require where we have a singular point. It's the first one and the third one. Okay, now let's go discussing a little bit what a singular point really means. I see I did it a little bit different. So let's go first to the discussion of the singular points. It doesn't react. Where is the mouse? Ah, now it seems. Okay. Sorry. Let's discuss the singular points first. Can I go back another? Okay, singular points of differential equations. Well, the definition I've already given. Singular point is when the coefficient of the highest derivative vanishes. Well, this has a consequence. And the singular points may be split into two groups, whether it's a regular singular point or an irregular singular point. If you have an irregular singular point, then you only have diverging solutions. So if you have a singular point where the coefficient of the highest order derivative vanishes, you have two possibilities. Either this is a irregular singular point, and then all solutions of the differential equations will behave badly because they diverge too. If it's a regular singular point, then there are some solutions of the problem which diverge at this point, but there are also solutions which do not diverge at this point. So you may have some solutions which remain finite. Of course, for physical reasons, we would not like to have an irregular singular point, but otherwise we would always have solutions which diverge, which we cannot interpret. For regular singular points, for physical reasons, we would then have to select those solutions of the equation which have a regular behavior or non-diverging behavior. So in that case, we have the chance to get physically interpretable solutions, but we have to make sure that our solution procedure excludes the irregular contributions. So once we by mistake have a contribution of these irregular solutions, then this will spoil our solution concerning the physics completely. Okay, you agree? For physical reasons, we always need regular solutions. And in those cases where we have a regular singular point, we have to select those regular solutions from the solution space and exclude the irregular possibilities. Okay. Irregular singular points are excluded in physics. We don't want them at all, and we are dealing with we would like to deal only with the regular singular points. Okay, let's give an example, a very simple example of regular and irregular singular points. Well, what does it mean? The an irregular singular point is found once the power by which the coefficient of the highest derivative vanishes with x is higher than the order of the differential equation. So if we have an mth order differential equation, the highest order will be dym by dxm, and the coefficient vanishes at the singular point with power n. So we have xn times dmy by dxm, and if n is bigger than m, then we have an irregular singular point. If n is smaller or equal, and sometimes equal to m, then we have a regular singular point, and we may expect that some of the solutions will be regular. Okay, that's what I said just before. So let's consider now an example. So these regular singular points are those where xn times dm by dxm has n smaller than m. Of course, the m has to be bigger than 2. We have to consider equations with an order m bigger than 2. Okay. If in the cases regular solutions are required, not for physical reasons, they have to be selected, and to be selected by which means? By the means of boundary conditions or initial conditions. Okay, we can select or we can exclude irregular solution or select the regular parts of the solution by applying or by requiring appropriate boundary conditions. So now let's make a let's consider two examples. For an irregular singular point, we consider the differential equation of first order x to power alpha times dy by dx plus y is equal to 0. A simple first order equation. How do we solve it? We solve it by separation of variables. So bring the y variables to the left hand side and all the x variables to the right hand side. We have dy over y is minus x to power minus alpha times dx. Integrated, the left hand side will give a log y, the right hand side gives x to minus alpha plus 1 divided by minus alpha plus 1. Okay, then take the exponential and we have the solution. Take the exponential, then y is a constant times the exponential of this quantity, which is x to exponential of x to 1 minus alpha, and alpha not equal to alpha divided by alpha minus 1. Alpha should not be 1. In that case, we have another solution given here. So you see, once alpha is bigger than 1, that means it decays faster than the order of the differential equation. You have a diverging solution here. If alpha is bigger than 1, this diverges, and of course the exponential diverges too. You have a diverging solution for alpha bigger than 1, and if alpha is smaller than 1, then you have a nice behavior, so it's no longer diverging. This is an example for an irregular or regular singular point, depending on whether the coefficient of the highest derivative vanishes faster or less fast than the power of the order of the differential equation, which is here of first order. That's as an example, or the distinguishing between regular and irregular singular points. Okay, now let's get to another example, which is closer to the case we consider for stellar pulsations. Let's take the following second order differential equation: x squared times d2y by dx squared plus x times the first derivative plus some constant b of the function itself is equal to 0. Well, You can try as a solution a power law. That means you try a solution in the form y is proportional to the power beta of x. Then you can derive the first and second derivatives. And if you insert this into your differential equation, you are left with an equation for beta, for the power by which this function, for the power of which, by the power of the function x to beta. If you find a quadratic equation for beta, and you end up with beta equal to plus minus the coefficient b. B should be smaller than unity to allow for real solutions. So the general solution will be a superposition of two power laws. One goes with x to plus square root of minus beta, and the other one goes with x to minus square root of minus beta. Okay, so the general solution of this equation will be C1 times x to the power square root of minus beta plus C2 times x to the power minus square root of minus beta. X equal to 0 is a singular point because in this case the coefficient vanishes like x squared, and this is the second order, so it vanishes with the same power of as the order of the differential equation. So it's a singular point, and it's a regular singular point because it does not decay faster than the order of the differential equation. So in that case we have both irregular and regular solutions, and we have to, if we want to have only regular solutions, we have to exclude the irregular parts by appropriate boundary conditions. Okay, how do we do this? In that case, we have the general form. Well, of course, obviously, that one diverges for x equals to 0, and this remains regular. We have two solutions, two fundamental solutions. One of them is well behaved, and the other one diverges. So we would not like to have this solution. That means, as a boundary condition, we have put C2 equal to 0, and we are left with the regular part. This should demonstrate you that you can select between irregular and irregular parts simply by applying appropriate boundary conditions. And here you do it simply by requiring that C2 is equal to 0. Okay, this situation is present once we consider our perturbation equations for the radially symmetric pulsations and perturbations. So let's go and to determine the right boundary conditions which exclude irregular solutions and at the same time guarantee that our solutions are interpretable in terms of physics in the sense that they remain finite. So we have to think of irregular solutions of our perturbation equations, and we have to select the well-behaved non-diverging solutions. So let's go back. Here it is. I have done this explicitly because many people are not aware of the fact they have to care about singular points and about to care for the consideration of appropriate boundary conditions for equations. And once you don't do it, then you will end up with trouble, because then you always capture some diverging contributions, and that will spoil you the entire solutions here. Okay, well, let's go a bit. I would like to see the. Here we go. A little bit up. Just. Okay, now it works. Okay, here we are. So we brought it already, the C1 and C4 is brought to the left-hand side. So what would be the appropriate boundary conditions then, or the appropriate conditions for this differential equation which excludes the irregular solutions? Well, if we ask for finite solutions and we bring the C4 to the left-hand side, then simply the left-hand side would be 0 for regular solutions. So what we need to adopt or to require in order to exclude the irregular solutions and keep the regular ones would be that for the center of the star, the right-hand side or the bracketed terms has to be 0. So only by the boundary conditions 3 zeta plus alpha p minus delta t at the center, we can guarantee that our solutions remain finite and that our solutions are physically interpretable. The same is true for the third equation. Bring C1 to the left-hand side, requiring L dash t and p to remain finite. Then this term will vanish on the left-hand side, and the bracketed term on the right-hand side needs to vanish. If we don't require that these two bracketed terms vanish in the center of the star at r equal to 0, which is the center or the one of the boundaries of our integration domain, then we will capture irregular solutions which spoil everything. Okay, keep this in mind. It's important to consider singular points whenever they are there. Simultaneously, if you are asking yourself what will be the boundary conditions for our system, they help you to select at least one class or a subclass of boundary conditions, which in this case have to be adopted. You are not free to choose any other boundary conditions in the center, because if you want to have regular solutions, you are forced to have these boundary conditions of vanishing brackets above and down. There. Okay, so let us proceed further with the discussion of this equation and its solution. Well, let's consider first. There are time derivatives in here, in our equation. Time derivatives at two places here. We know all our coefficients here are time independent, and only the dependent variables t, zeta, and p are time dependent. Well, now one can get a solution of this equation simply by separating the time and space dependence, by assuming the time dependence to be proportional to an exponential. Okay, that's done in the next step. So this partial differential system, it's a partial differential system with respect to the mass m and the time t, can be separated into a ordinary differential system with respect to the mass coordinate in space, and by separating the time dependence according to an exponential, we can get rid of the time dependence and we can solve it then only in terms of log p or the mass mr. So what we try as a solution is that q, which now depends on log p naught rather than mr as before, and time t, there is a part of the solution which only depends on the spatial coordinate. Let's denote it by q hat, only a function of the spatial coordinate log p naught, time an exponential of I sigma tau. This is the time dependence of the variables which we assume. Well, then the derivative with respect to the time derivative of a quantity with respect to the time tau would then result in the same function times a factor of I sigma. So time derivative of a function will then, the time derivative will not act on this part, it acts on the exponential, and the time derivative of the exponential will give the exponential times the inner derivative, which is I sigma. It's just a multiplication with the quantity I sigma. The second time derivative will be then give the a multiplication twice. That gives a multiplication with minus sigma squared. This sigma is called the complex, is a complex quantity. It's called the complex eigenfrequency or the complex eigenvalue of our system. So it may be written in terms of a real part, sigma r plus I sigma I. What does this sigma, these eigenvalues tell us? Well, let's consider the time dependence explicitly. Then Q will be given by Q hat times the exponential. Now take the real part. The real part, it's I sigma r times tau minus sigma I times t. Well, this is an exponential which increases or decreases depending on the sign of sigma I. So the sigma I gives us some measure whether the perturbation will. Oops. Now we are in the wrong. Whether we have a decaying or exponentially increasing function. Okay, so let's split into two parts. This is the spatial the part which denotes the spatial dependence, and we have an exponential of a real quantity. So we have exponential decay if the sign of sigma I is bigger than 0. This would correspond to stability. Then the system will come back to its initial state. If sigma I is negative, then we have an exponentially increasing amplitude of our perturbation. This would correspond to an instability. And this, the second term, can be written in terms of cosine and sigma RT, cosine sigma RT and sinus sigma RT. This corresponds to an oscillation with frequency sigma R. So once we know this eigenfrequency or eigenvalue, then we have the oscillation frequency of our pulsation. And once we have the sigma I, the imaginary part, we can decide whether the perturbation will exponentially increase in time or if it decays exponentially back to its original state. If sigma I is 0, that's called a neutrally stable situation. Neutrally stable, the amplitude of our pulsation or the oscillation amplitude will remain constant. This is the so-called neutrally stable situation. Okay. I have some difficulties with this mouse. Okay, that's what I already said. Exponential growth if sigma I is smaller than 0. Consequences is the derivative. One derivative with respect to tau is equivalent to multiplication with I sigma. The second derivative is given by multiplication with minus sigma squared. Now, in the once we adopt this time separation procedure, then we can cancel all the exponentials in the original equations, because the time derivatives here will result simply in the exponentials will remain by this differentiation. It just gives a multiplication with I sigma here, and all the dependent variables will contain the exponential factor, which we can simply cancel on any of these dependent variables. So that cancels, and we are left with an equation which acts only on the spatial part of the solution, and that means we are left then with an ordinary differential equation which only refers to the spatial coordinate. And for simplicity, we will omit now in the next slides, we will omit the hats denoting the spatial part, because we are now only dealing with the spatial parts of the perturbations. Okay, so next step we need to consider has to do with our boundaries. Well, solution of this LNA problem requires 4 boundary conditions. We have four equations, so we need to specify 4 boundary conditions now for ordinary differential equations. Well, the outer boundary of our model is the photosphere, and for the photosphere we usually have the validity, or we require the validity of Stefan Boltzmann's law, saying that the luminosity is proportional to r squared times the effective temperature to the 4th. If we linearize this boundary condition, this will give us relative luminosity is 2 times, this is the exponential here, 2 times the relative Lagrangian displacement plus 4 from the exponential here, 4 times the relative Lagrangian perturbation of the temperature. Well, the other usual boundary condition we adopt is we have at the outer boundary the pressure is almost 0 or very small, or you can argue above the outer boundary of our star will be close to vacuum. Vacuum cannot take up any stress or any pressure, so the pressure perturbation has to be 0. This is the so-called force-free boundary condition, which we assume already at the photosphere, even if the pressure is not exactly 0. So this is an approximation. We take the Lagrangian. Keep in mind we are in the Lagrangian picture. The Lagrangian pressure perturbation is required to be 0 at the outer boundary. Why do we say that there is an ambiguity? Actually, there are many boundary conditions available for the outer boundary, because the outer boundary of our model is not the outer boundary of our star. If it was the outer boundary of our star, we would be fixed by, or we would have to require some physical boundary conditions. And here, these boundary conditions sound very reasonable, but they are not unique. They are not unambiguous, because there you can, by other arguments, you can adopt other boundary conditions. So keep in mind that the boundary conditions for our perturbations equations at the outer boundary are not unambiguous. So they may vary from authors to authors. Other authors use different boundary conditions. The only thing one can do, one can study the influence of the boundary conditions on the solutions. And if the boundary conditions are found not to matter very much, then we can be sure that we have got the right physical answer. This would be the only way or the more reliable argument that we are dealing with the right stuff here. But in concerning the ambiguity of the principal ambiguity of the boundary conditions, we cannot exclude any other boundary conditions which seems to be reasonable other than these 2. Okay, keep in mind there's an ambiguity, and if you want to be sure whether your results are physically reliable, you should try several boundary conditions and compare the results. If the results compare or are not too much affected by the boundary conditions, then you are sure you have done the right physics. Okay? It's more easy for the inner boundary conditions. We have already touched that problem. Well, these are the 2, again in more detail. Inner boundary, which occurs at 0 radius for a complete stellar model. Then we bring the coefficient C1 or C2 to the left-hand side, because this coefficient vanishes, 1 over C4 vanishes. We need to require, for regularity reasons, that 3 zeta plus alpha p minus delta t has to be 0 for regularity requirements. So left-hand side has to be 0, as explained before. Here we are. Can we shift down? Okay, So the one boundary condition, one of the regularity conditions was 3 theta plus alpha p minus delta t equal to 0, and the next one would then be considering the next equation where we have a diverging coefficient. This is this is the energy equation given here. So C1 goes like 1 over r squared. Also the regularity condition would then mean that the bracketed terms 1 over nabla adiabatic times t minus p has to be 0. So regularity at r equal to 0 provides two boundary conditions. So we have two boundary conditions on the surface of the star at the photosphere and two regularity conditions at the center. The regularity conditions at the center are unique because once you require the solutions to be regular, you are fixed to these two boundary conditions. There is no ambiguity, so this is very fine. You don't need to care about this anymore. This, of course, is only true if you include the very stellar center in your computations. If you only consider the envelope, you have to invent some auxiliary boundary conditions at the inner boundary of your model. Okay, so we have four boundary conditions for our equations. I again have okay. So can I go down a bit? So these boundary conditions are unambiguous, and you are restricted to use them. Down. Can you go downward? Okay, we have already discussed it, so we can go further down. Down. Okay, so a little bit. So we end up with the following system of equations, which are now ordinary differential equations. This is a differential system of fourth order with real coefficients. We have already discussed the various coefficients with two places where time derivatives have occurred before. This is the acceleration term, which now contains the sigma squared. This is the second derivative. And in the energy equation, the place where the thermal timescale comes into play, this is a multiplication with I sigma here. And we have, for the fourth order system, we have four boundary conditions, two well-defined regularity conditions at the center, and two less well-defined boundary conditions at the surface. So we have now a so-called fourth order boundary eigenvalue problem. So we have two boundary conditions at any of both sides of the integration interval, and the problem contains a parameter which is the complex eigenfrequency sigma appearing at two places of the differential system. We have four boundary conditions, the regularity conditions at the center, and pressure-free surface, and the Stefan Boltzmann law at the surface of the star. Okay, the question then, we have enough boundary conditions, we have the equations. Do we have a solution? A mathematician will always first ask, does the problem have a solution? Before he constructs a solution, a mathematician will always ask, do we have a solution to the problem? What would be your answer? Do we have a solution to this problem? We want to solve it. But does it have a solution? Well, the answer is no. This problem in general has no solutions. Why? Well, if we put, rather than putting two boundary conditions at the center and two boundary conditions at the surface, when we put all the four boundary conditions on one side, does it have a solution? Still not? Yes, it has a solution. It always has a solution for any values of the parameters. So the problem is that we have a boundary value problem where we fix the boundary conditions not only at one place. This would be a so-called initial value problem. So you give to all of the quantities, you give an initial value, and then you can proceed. This will always have a solution. But once we start with two boundary conditions at one place, and possibly taking two other arbitrary boundary conditions, we will not be able, or in general, we will not hit the boundary conditions prescribed at the second boundary. This is not possible. So we have to look whether we can construct a solution at all, and then how to calculate the solution, and what, for instance, what to do with the remaining parameter which is contained in our equation. There is one open or one free parameter still remaining in our equations we haven't really determined. The question is, could this parameter help in finding a solution, or could this parameter adjust it in such a way that it guarantees the existence of a solution? Strange situation. This equation in general has no solution, together with the boundary conditions. So the boundary conditions really matter. In particular, the way in which we prescribe these boundary conditions is responsible for the solvability or the non-solvability of the equations. Well, to illustrate this rather counterintuitive argument, I would like to show a similar system which is in some sense related also to our stability problem or our pulsation problems found here. So the task, well, this is anticipating, determine the values of the parameter sigma for which a solution does exist. A solution means equations plus the boundary conditions. Without it, if you change the boundary conditions from boundary to initial value, we will always have a solution. This sigma would not be determined. But if you have a boundary value problem and use the sigma as a parameter by which you can guarantee a solution, then you can end up with both satisfying the solution and determining the spectrum of eigenfrequencies. Okay, the example or the analog of this system is again our well-known organ pipe. So let's consider the corresponding problem for our organ pipe of length L. The organ pipe contains air with constant pressure, P0, constant density, and it's similar to our star. It's a one-dimensional configuration. We had, in the introduction, we already considered the organ pipe as an analog of our pulsating stellar system. We use independent Eulerian variables x and t. This time we go to the Eulerian variables, and we consider the Eulerian perturbation problem, Eulerian perturbations of mass and the momentum equations. Well, do I have to stop here? Yeah. Okay, let me just introduce first for the equations. Well, mass and momentum equation needs to be considered here. Mass conservation is the partial derivative, the Eulerian time derivative of density plus the divergence of rho times v. This is the mass conservation equation. Well, rho naught is equal to, we do the same procedure of linearizing these equations. So rho is given by the constant rho naught, the time independent density, plus the perturbation of the density. Now it's the Eulerian perturbation denoted by this tilde. So we have d rho tilde by dt, because d rho naught is time independent, plus the divergence now reduces simply to a derivative with respect to x, is given by the product of density times velocity. In the stationary organ pipe, the velocity is 0, so velocity is itself a first order quantity, so we only need to multiply it with the stationary value. Similarly, for the acceleration, the v times nabla v term is not considered, because it's a quadratic term in the velocity, and the velocity v naught of the unperturbed system is 0. So we are left with rho naught times the derivative, the Eulerian derivative of the velocity perturbations with respect to time. On the right hand side we have the pressure. Well, the pressure gradient in the original organ pipe is 0, so this reduces to the gradient of the pressure perturbation minus dp tilde by dx. Well, there is a relation between the pressure perturbation and the density perturbation, which is given by the p of rho. We assume that pressure depends only on density. P is only a function of density. This can be done, for instance, if we assume that the changes of state are fast enough, that we have an adiabatic change of state, then the pressure is only a function of density, and we can write it in terms of the density only. Then p tilde is simply dp by d rho, this derivative of pressure with respect to density, times the rho tilde, the perturbation of the density. Well, dp by d rho is nothing but the sound speed squared, and we are left with minus c squared, c sound squared, times the derivative with respect to the spatial variable x of the density perturbations. Now we replace the density perturbation by the velocity perturbation simply by taking this value for the density perturbation, or differentiating this twice with respect to time, and then replacing the d rho tilde by dt by this quantity, by the divergence of x. Then we end up with a single equation for the velocity perturbation, which is given as the result, and I will stop here then. Can I get a little bit down here? Okay, so we differentiate this twice with time, then we are left rho naught times second time derivative of velocity perturbation is minus c sound squared, d by dx, the derivative of the density perturbation with respect to time. Take the result from the mass conservation, then this will be rho naught c sound squared times rho naught times the second derivative of the velocity perturbation with respect to the spatial coordinate, or in the end we end up with the acoustic wave equation for our organ pipe, which is given by second derivative of the velocity perturbation minus sound speed squared times the second derivative of the velocity perturbation with respect to the coordinate x equal to 0. So this equation would then be the analog of our fourth order system describing the pulsations or sound waves within a star. Let's consider how we determine the frequencies of the organ pipe, and then let's go back and consider the same procedure then what we'll do determining the eigenspectrum of a star. So this is simply the basic equation for our organ pipe. to be compared to the perturbation equations of the star, and we will see how we determine the spectrum here, how it comes about that we have a boundary eigenvalue problem, and how that and we'll see that this boundary eigenvalue problem in general will not be solvable, and under which condition which we can solve it, and at the same time determine the spectrum of the possible eigenfrequencies, and here the possible spectrum of our organ pipe. Okay, that will be done in the next lecture. Thanks.